All right, today we are going to crack the code on a classic logic puzzle you'll see on the GCSE computer science paper. You know the one? You see a truth table like this, and it just looks intimidating. Well, if that's you, you're in exactly the right place. We're going to break this whole thing down step by step so you can look at these things and solve them with total confidence. So here's our game plan. We'll start with the puzzle itself. Then we'll get to know the logical operators. Those are kind of our tools for the job. Then we'll solve the whole thing together. After that, we're even going to check our work against the official mark scheme before we zoom out and see why this simple little table is actually the secret language behind almost all of our modern tech. Okay, here it is, question 5A, pulled straight from an OCR exam paper. But let's not think of this as some scary test question, okay? Let's treat it for what it is, a logic puzzle. We've got a set of inputs, we've got a rule to follow, and our one job is to figure out the output. Simple as that. And this is our puzzle board. Over on the left, we've got our three inputs, A, B, and C. You'll see every possible combination of zeros and ones, which really just stand for false and true. Our mission, should we choose to accept it, is to fill in that final column, P, by following this one rule. P equals A and B or C. Now, I know it might look a little complicated, but it's actually built on just a couple of really simple ideas. So to solve this, we first need to understand our tools. And in this case, our tools are just those keywords in the expression, and or. These are what we call logical operators. This expression right here is basically our instruction manual. It tells us exactly what to do and in what order. We just have to know what those keywords actually mean. First up is the AND operator. You can think of AND like a really strict security guard at a club. It will only give you an output of 1, or true, if both A and B are true. If either one of them is false, or if they're both false, nope, the output is a firm 0 or false. Next up is the OR operator, and honestly, it's way more relaxed. It'll give you an output of 1, or true, if at least one of its inputs is true. The only possible way to get a 0 or false out of an OR operation is if both of the inputs are false. And just like in math class, there's an order of operations. The parentheses are a massive clue here. They are screaming at us, telling us exactly where to begin. We absolutely have to solve the A and B part of the expression first before we do anything else. All right, we've got our puzzle, we've got our tools, and we've got our rules. I think it's time we put it all together and actually solve this thing, row by row. Let's do it. Okay, here's a little pro tip to make our lives way easier and keep everything nice and organized. Let's add a temporary helper column to our table. In this new column, we're just going to write down the result of the bit in the parentheses, A and B. This is a great trick because it breaks the one big problem into two smaller, much simpler steps. Okay, let's fill in that helper column. Now remember, for this step, we only need to look at columns A and B. That's it. And we're using that super strict AND rule, right? The output is only a 1 if both A and B are 1. So if we scan down the rows, we can see that only happens in the very last two rows. For every single other row, the result is 0. And now for the final step. The best part is we can completely ignore the original A and B columns now. We're just focusing on our new helper column in column C. And this time, we're applying that relaxed OR rule. So for the first row, we have 0 from our helper column or 0 from column C. That gives us 0. Second row, it's 0 or 1, which gives us 1. We just keep doing that all the way down the table. And just like that, our final P column is done. We're feeling pretty confident in our answer, but in an exam, the only thing that really matters is getting the marks. So let's do the smart thing and compare our solution to the official mark scheme from OCR. And there you have it. Let's compare our completed P column to the official answer, and yep, it is a perfect match. That right there is a full marks answer. We've officially cracked the puzzle. But wait, for anyone taking this exam, how the marks are given out is just as important as the final answer. And the official mark scheme says you get 1 mark per group of 2 rows. This is fantastic news for us. It means you don't actually need a perfect table to get points. The examiner marks your first 2 rows, then the next 2, and so on. So get this, even if you make one tiny mistake in the very last row, you can still get 3 out of the 4 marks. It just goes to show you why being neat and systematic really pays off. So we've solved the puzzle, we know how to get the marks, but why? Why does any of this even matter? Well, let's connect this abstract little puzzle to the very foundation of the technology we're using every single day.
And that's a totally fair question. It's so easy to look at this and think, when am I ever going to need to do this again? Well, the answer might surprise you because you are using this logic right now.
See a diagram like this? This is what our little Boolean expression A and B, or C, actually looks like in the physical world. Each of those symbols is a logic gate, which is basically a microscopic electronic switch. And that truth table we just solved, it is the literal blueprint an engineer would use to design and build this exact circuit.
And we're not just talking about one circuit. We're talking millions, sometimes billions, of these tiny logic gates packed onto every single computer chip. They are the fundamental building blocks that power literally everything, from the processor in your computer, to how a database finds information, to how AI makes decisions, and even the mechanics inside a video.
So here's the big takeaway. By solving a table like this, you're learning the fundamental language that all modern digital technology speaks. Every single complex system, every app, every device, it's all built from billions of these incredibly simple true or false decisions. And this all points to a much bigger idea. And it leaves us with one final question to think about. If a device, as mind-bogglingly complex as a computer, can be broken down into these simple, understandable rules, what other complex systems in our world, in science, in society, maybe even in our own behavior, are also just simple rules, stocked up, just waiting for us to crack the code?